Hello, I am Sapna Davis of EC Department, Rajagiri School of Engineering and Technology. Non-metric methods. If feature vectors are real valued or discrete valued numbers, we can measure the distance between such vectors. And there are classification problems involving nominal data. For nominal data, descriptions can be discrete and without any similarity or ordering. Examples of nominal data include a country, gender, race, hair color, etc. of a group of people. A common approach is to specify the properties by a property D tuple. Example, describing a piece of fruit by the four properties like color, texture, taste, and smell. Then a particular fruit can be described by the four tuple red, shiny, sweet, and small. Next, decision trees. We can classify a pattern through a sequence of questions in which the next question asked depends on the answer to the current question. Since all questions can be asked in a yes or no, or true or false, or value or property, it does not require any metric. Sequence of questions is displayed in a directed decision tree. The root node is displayed at the top, connected by successive links or branches to other nodes. These are similarly connected until we reach a terminal or leaf nodes. An example of a decision tree is shown, and this is used for the classification of fruits. The classification of a pattern begins at the root node, which asks for the value of a particular property of the pattern. Based on the answer, we choose the link to a subsequent or descendant node. The next step is to make the decision at the subsequent node. We continue until we reach a leaf node, which is no further question. Every leaf node bears a category label, and the test pattern is assigned the category of the leaf node reached. One benefit of trees over other classifiers like neural networks is interpretability. It is straightforward to get information in such a tree as logical expressions. We can interpret the decision for any particular test pattern as a sequence of decisions along the path to its corresponding leaf node. Large trees are often quite complicated and must be reduced to aid interpretation. Trees lead to rapid classification, employing a sequence of typically simple queries. Trees provide a natural way to incorporate prior knowledge from human experts. Next, we'll see the tree growing process. We use training data to grow a decision tree. Consider a set D of labeled training data, and a set of properties are decided to discriminate the patterns. Now, these properties to be organized as tests into a tree. Any decision will progressively split the set of training samples into smaller and smaller subsets. If all the samples in a subset are of the same category, then it is pure and that portion of the tree can be terminated. There is a mixture of labels in each subset at a node. Then we have to decide either to stop splitting and declare a node to be a leaf, or select another property and grow the tree further. There are 6 general kinds of questions arise. First one, should the properties be binary valued or multi-valued? That is, how many splits will be there at a node. Second one, which property to be tested at a node. Third one, when should a node be declared a leaf? Fourth one, if the tree becomes too large, how it can be made smaller and simpler, that is how it can be pruned. Fifth one, if a leaf node is impure, how the category label can be assigned. And sixth one, how the missing data can be handled. Next, you'll see the number of splits. Every decision outcome at a node is called a split, since it splits a subset of the training data. The root node splits the full training set. Every successive decision splits a subset of the data. Number of splits is set by the designer and can vary throughout the tree. The number of links descending from a node is called the node's branching factor or ratio. However, every tree can be represented using binary decisions. A tree of binary decisions is shown. Test selection and node impurity, that is deciding which property to be tested at every node. With the non-numeric data, there is no geometrical interpretation of how the test at a node splits the data. But for numerical data, we can visualize the decision boundaries as shown. The fundamental principle in tree creation is simplicity. We prefer decisions that lead to a simple compact tree with a few nodes. We try to find a property test T at every node n that makes the data reaching the descendant nodes as pure as possible. Let I of n denote the impurity of a node n. The most popular measure is the entropy impurity or information impurity. It is given as a In equal to minus summation p omega j log p omega j. P omega j represents the fraction of patterns at node n of category omega j. If all the patterns are of the same category, the impurity is 0 and maximum when the different classes are equally represented. Another definition of impurity for a two-category case is called as the variance impurity, since it is related to the variance of a distribution of a two categories. I of n equal to p omega 1 multiplied with the p omega 2. A generalization of the variance impurity for two or more categories is the Guinea impurity, and it is given by In equal to summation I not equal to j p omega I p omega j, and this is equal to 1 minus sigma p square omega j. This is more strongly peaked at equal probabilities than the entropy impurity. Misclassification impurity at node n is In equal to 1 minus max p omega j. This measure is the most strongly peaked at equal probabilities as shown. Choose the tester that decreases the impurity as much as possible. The drop in impurity is defined as delta In equal to In minus PL INL minus 1 minus PL INR. NL and NR are the left and right descendant nodes. INL and INR their impurities, and PL is the fraction of patterns at node n that will go to NL for property test T. Then the best test maximizes delta IT. We continue to split tree further to get the lowest possible impurity at the leaves. But there is no guarantee that the impurity at the leaf node will become 0. The overall goal is to find the best place supporting the data of a C classes. Let the classes be C equal to omega 1, omega 2 up to omega C. At every node, the decision splits the categories into C1 and C2, where C2 equal to C minus C1. For every split test, we compute the change in impurity delta IS C1. We find the split test star C1 that maximizes the change in impurity. Entropy impurity is frequently used, though Guinea impurity is also significant. Multi-way splits. In such a case, the change in impurity delta IS equal to In minus summation Pk Ink, where Pk is the fraction of training patterns sent to node Nk and summation Pk equal to 1. Drawback: decision with the large B are favored over small b always because it reduces the impurity. To avoid this, the change in impurity must be scaled. When to stop splitting during the training of a binary tree? If we continue to grow the tree fully until each leaf node corresponds to the lowest impurity, it results in overfit. In rare cases, each leaf corresponds to a single training point. Conversely, if splitting is stopped too early, then the error on the training data may not be low and hence performance will be poor. To stop splitting, one traditional approach is to use cross-validation. The tree is trained using a subset of the data, say 90%, with the remaining 10% kept as a validation set. Continue splitting nodes in successive layers until the error on the validation data is minimized. Another method is to set a threshold value in the reduction in impurity. Splitting is stopped if split at a node reduces the impurity less than a threshold. That is, if maximum of del I is less than or equal to beta. This method has two main benefits. Unlike cross-validation, the tree is trained using all the training data. Leaf nodes can lie in different levels of the tree, which is desirable when the complexity of the data varies. Drawback: difficult to set the threshold because no simple relationship between data and the performance. Another simple method is to stop when a node represents less than some threshold number of samples, say 10, or some 5% of the total training set. Benefit: size of the partitions is small in regions where data is dense but large when the data is sparse. Another method is to trade complexity for test accuracy by splitting until a minimum in a global criterion function alpha times size plus summation in for leaf nodes is reached. Here size could represent the number of nodes or links and alpha is some positive constant. The size of the tree is a measure of the complexity of the classifier itself. Difficulty: to set alpha, no simple relationship between alpha and the classifier performance. Pruning: stopped splitting suffers from the lack of sufficient look-ahead, a phenomenon called the horizon effect. The split at a node n is not influenced by decisions at n's descendant nodes. If splitting is stopped, node n to be declared a leaf, cutting off the possibility of a beneficial splits in subsequent nodes. A stopping condition can be met too early for overall optimal accuracy. Principal alternative approach to stop splitting is a pruning. In pruning, a tree is grown fully until leaf nodes have minimum impurity. Then all pairs of neighboring leaf nodes linked to a common parent node are considered for elimination. Any pair whose elimination yields a small increase in impurity is eliminated. Such merging of the two leaf nodes is the inverse of splitting. After pruning, the leaf nodes lie in a wide range of levels and the tree is unbalanced. Benefits of pruning: avoids the horizon effect. No training data held out for a cross validation. It uses all data in the training set, but greater computational expense than stop splitting, and for large training sets, the expense can be prohibitive. For small problems, the computational costs are low and pruning is generally preferred over stop splitting. Conceptually different pruning method is based on rules. Every leaf has an associated rule, that is the conjunction of the decisions from the root node to the particular leaf. Occasionally, some of these rules can be simplified if a series of decisions is redundant. Eliminating the irrelevant precondition rules simplifies the description. Benefit: reduced rule set may give improved interpretability. The last step is assignment of leaf node labels. Assigning category labels to the leaf nodes is the simplest step in tree construction. If each leaf node corresponds to the patterns in a single category, that is zero impurity, then this category label can be assigned to the leaf. Generally, either stop splitting or pruning is used, and the leaf nodes will have some positive impurity. Every leaf should be labeled by the category of the most data points represented. An extremely small impurity is not necessarily desirable since it can lead to overfitting.